Hey everybody, in this next video lesson we are going to begin the next unit on nuclear chemistry. Now nuclear chemistry is different than regular chemistry or chemical reaction chemistry because in chemical reactions it's all about movements of electrons and what are happening to electrons because electrons make bonds and bonds break and bonds reform, making new substances. Where nuclear chemistry has nothing to do with electrons, it all has to do with what's happening inside the nucleus between the protons and the neutrons. And so we're dealing with interactions of the nucleus, not interactions with electrons. Some observations about nuclear chemistry. First of all, it's always spontaneous. If a nuclear change is going to happen, it will do so spontaneously. Another thing about nuclear situations is that they are unaffected by temperature, pressure, or catalysts. These things will have no effect on a nuclear situation. Next, you can't change the rate of an actual process or even stop it. Nuclear chemistry happens at a defined rate, and once it starts, it will proceed to the end, and you can't do anything about it. The rate is unchangeable, but it can be predictable, which we'll learn about here in a few days. Finally, the chemistry of a nucleus is based on the stability of the isotopes. Isotopes, if you remember, are basically different versions of the same element. I'm looking at 3 isotopes of lithium down here. Each of them have 3 protons, which is this number in the lower left-hand corner. But the difference between these 3 isotopes is their mass, or their number of neutrons. This first one has 3 neutrons, this middle one has 4, and this last one has 5. And so we're looking at the stability of the isotopes to determine whether or not a nuclear decay or a nuclear reaction will occur. We're taking a look or focusing on individual isotopes of elements. This is different than chemistry up to this point because all the chemistry we've been doing has been assuming an average of all the known isotopes of an element, but in this case, we're taking a look at individual isotopes alone. I told you about 3 examples here with lithium, but other examples include carbon-14 and uranium-238. Now in chemistry, that deals with chemical reactions, we're always talking about atomic numbers and atomic masses, those sorts of things. But with nuclear chemistry, since we're only focusing on the isotopes, we identify the different isotopes by their mass numbers alone. So the atomic numbers are important, and you can determine the atomic number based on the symbol, but the mass numbers are what you can use to determine the different isotopes of a particular substance. Nuclear chemistry is all based on the stability of the isotopes. So when you're looking at an isotope and you're wondering whether or not it's going to be stable or not, what we're looking for is a ratio of the neutrons to the protons, which is what we call the A to Z ratio, where A is the number of neutrons and Z is the number of protons. For lighter elements, an A to Z ratio is pretty much 1-to-1. Lighter elements are defined by anything less than a mass of 20, so that is calcium, everything up to calcium. So the lighter elements, as we start down here, fall along this ratio of 1-to-1 neutrons to protons. But right about 20, you can see that the number of isotopes that don't follow the 1-to-1 ratio starts to veer away and get closer to this 1.5-to-1 ratio. So heavier elements tend to move closer to a 1.5-to-1 ratio of neutrons to protons, or in other words, as you get heavier, you need more neutrons compared to your protons in order to have a stable nucleus. If an isotope doesn't have a stable ratio, it will react in order to become more stable. It will respond by doing a number of things in order to achieve stability, which is something that we're going to talk about at a later date and time. We're going to finish up here talking about a concept known as radioactivity. Whenever the discussion moves from regular type of chemistry to nuclear type chemistry, the concept of radioactivity soon follows. But what is it? Radioactivity is the emission of rays from the nucleus of an atom when the nucleus becomes more stable. This is what is called radiation, and this is used in radiotherapy for things like treating of cancers, but it is also an unfortunate byproduct of things like nuclear reactions. And this radioactivity can be very dangerous if not controlled. The different types of radioactivity could be particles that are emitted from a nucleus, but it could also be energy. So, when you're looking at a nucleus that is unstable, it will respond in order to become more stable by either ejecting a particle or emitting some energy, and oftentimes both of these happen at the same time in order to achieve stability. The term radioisotope refers to an unstable isotope of an element. So if it's ever unstable, it is considered a radioisotope. And if it's ever a stable isotope, well, we just call it a stable isotope. In order to become a radioisotope, we have to observe an unfavorable proton to neutron ratio. If the neutrons and the protons in the nucleus are not in a comfortable situation, well, then it is unstable and it is then considered a radioisotope. Chances are, if it's a radioisotope of a small element, that means that the neutron to proton ratio is not 1:1, or if it's a heavier element, the neutron to proton ratio is not that 1.5:1 ratio, which we talked about on a previous slide. And when an unstable isotope is around, it exhibits radioactivity. Well, that takes care of this video lesson introducing the topics of nuclear chemistry and radioactivity. Thanks for watching.